Yeah, can you see the screen?
Yes.
Okay. So what we have discussed in the last class? Anyone? No one. Dissoprian, Guru Nishant. Everybody forgot what we have discussed, had discussed in the last class.
Sir, we mainly
Amal, yeah.
discussed about recrystallization, grain growth, after deformation, how it is formed and also.
But that one we discussed, I think 2 class or 3 class before, recovery crystallization. Yeah.
Yes, sir.
Okay. Okay. So maybe I will just tell some of the few points. So we discussed about the theory of plasticity, right? The basic background. Then we talked about the property, mechanical property of the metals, right? Then based on this mechanical, we went for the mechanism lead to failure, like for example, the elastic deformation, then plastic deformation, creep, then fracture, fatigue, then also other also like physical degradation or the microstructural changes, or maybe the corrosion, oxidation. These are also we have talked, right? You remember this thing?
Yes, sir.
Okay, so then we talked about the mechanical behavior, because if you know the mechanical behavior, then we can understand the whether it will be like the elastic mechanism or the plastic mechanism. Okay, so based on the mechanical behavior, we have talked about again elasticity and plasticity, then fatigue, then creep, and then fracture. So based on this, I have given a few examples also, like with some schematic diagram. Then we talked about the recoverable, or maybe the elastic, or maybe the permanent or plastic deformation process. Okay, so we talked about the instantaneous, then what is the related to the time dependent, based on the time actually how we can classify. For example, if you remember, one is viscoplasticity, then viscoelasticity, unelasticity. These are also we have covered. And then the basic mechanism also we have discussed about the plastic deformation. Okay, so how we will tell, if you want to plot the diagram of engineering stress and engineering strain, so what should be the plastic strain, and then how much force you are giving, so that initially it will be elastic, then you have the elastic and the plastic zone, or elastic or the plastic region, and then when you are removing, so some load, whatever the elastic part this is removing, then other part it will be like permanent or plastic deformation, right? And then some of the property like yield strength, tensile strength, then you have the toughness, ductility, resilience, and then hardness. These are also we have covered. Then the common type of deformation, what we have talked in the earlier classes also, like the tension, compression. Only I have added there torsion, right, including the bending and shear. These are also we have covered, right? Yeah. Okay. So today you just got the rough idea of what we have discussed, right? Okay. Amal, anyone? Am I audible?
Yes, sir. Yes, sir.
Yeah. Okay. Okay. So today we will talk about the more detail about the mechanisms or the modes of plastic deformation. Okay. So I put in a elaborate way the schematic diagram what we had discussed. Maybe I will just go back and the previous. If you want to go back, what this slide actually I have shown you. 1 second. Yeah, this thing, this slide I have talked about the mechanism or method by which a material can fail. Okay, but now we are not going in detail all the other part, because if we'll go in detail, I think we cannot finish anything. So we'll stick on, or we will stock on in somewhere. So we have to think about this one, because we are only thinking about the plastic deformation here, because this course is metal forming or plastic deformation. So we are not covering elastic deformation, fracture, fatigue. We are not covering anything. Just I want to show that what are the availability are there. Okay. So just only we will go about the plastic deformation. So only the slip initially we have to go, because in our syllabus only slip is there, but also at the same time also I will talk a little bit of twinning maybe in the next class, or maybe today if we have time. Then you will understand what is the slip and what is the twinning, right? Is it okay?
Yes, sir.
Yeah. Yeah, so what I mentioned here, the plastic deformation in crystalline. So because you have to understand, there are two kinds of materials actually we are thinking about. So we are mentioning here the crystalline material, then one is amorphous material. Maybe I do not know whether you know or not. So I put a small definition on how to define the crystalline materials. Have well-defined edges because your edge will be well-defined. So and the diffract X-rays and tend to have a sharp melting point. Okay, any kind of material, for example, copper or maybe silver, these are known as the crystalline material. But if you want to, because this amorphous material is, for example, for you probably it will be a little new, or maybe some people they have known this one or they are aware of this. So it has a irregular or curved surface because if you will compare to the crystalline, crystalline is the sharp edges or the sharp surface, but whereas the amorphous it has the curved or the irregular surface. And also it melt over a wide range of temperature. You cannot tell that only this material it can melt in that particular temperature. But in case of a crystalline material, for example, iron, let's say if you are talking, so you can tell that in this temperature, maybe plus minus 5 degrees, that is different. Generally, if you will tell that at that particular temperature, the material can melt. So this is the basic difference between crystalline and the amorphous material. So now when we are talking about the plastic deformation in crystalline material, so we have the one is slip, the dislocation motion, how the dislocation actually it can move from one place to another. Then only we'll find the plastic deformation. Then second one is twinning, and the third one we have the phase transformation, and fourth one we have the creep mechanism. But again, we are not going here in detail of the phase transformation because this is a separate subject. If you want to go in detail, phase transformation. Then also at the same time, if you want to go for creep mechanism, these are also a separate chapter. So we are not going detail in that. We will only stick on the slip. This is the most important because in our syllabus this is covered, and also twinning I will tell a little bit of things. Okay, so I mentioned here the plastic deformation in crystalline solid is accomplished by means of various processes mentioned below, among which sleep is the most important mechanism. Okay, so whenever we are thinking about the sleep is the most important mechanism, and also at the same time twinning also it will cover some part of mechanism, but this depends upon again the material, or the depends upon the material. So why that's why I told what is the basic meaning of the crystalline material and what is the basic meaning of amorphous material. And when we are using that different kind of material, again your process and everything it will be different, right? So now I just want to show that how actually it happens, or how the dislocation actually, or with the help of the sleep, how this dislocation and the whatever in the material you have the dislocation, how it will move from one place to another, or how it will shift from one point to another point. So what is the basic concept? So I mentioned here the sleep is the most important mechanism of the plastic deformation. At low temperature, especially the BCC metals, twinning may also become important. So I'm not sticking on only sleep, but at the same time also you can find in somewhere or in some cases twinning also one more advantage or one more process you can find the motion or the dislocation motion. So if you'll see the schematic diagram, so we know the caterpillar, right? So the way the caterpillar is working, so you will find in that similar way also your dislocation will move from one place to another. Okay, so what is actually a dislocation? So dislocation is a disorder in the crystal lattice or disorder in the metal piece, for example. So here you can see the initial position. For example, just I put the caterpillar on the top so that you can understand how it is moving here. So if you have a material piece or the crystal structure here, so you will find maybe you asked me how you are changing or how you are removing the shear stress, whatever the shear stress inside, how we are moving, how we are replacing. Overall, the technique, whatever we have discussed about the heat treatment or maybe the hot forging, everything we have discussed. But now the mechanism, how actually it is happening, how in which way it is happening. Okay, so if you have some shear stress or internal stress inside, so you will find this kind of structure. So that means all your the atoms or the crystal lattice, it will not in a similar order. For example, in the last line. Okay, so you have to find in the similar order. But if you cannot find some similar order, that means some shear stress or maybe some internal stress is there inside. So that means if you have this kind of internal stress here, or maybe the shear stress or the disorder there, so you will find the lattice structure is like this. Okay, it is not a straight. And the moment you are giving some force or giving some or you are applying some force there, so how it will happen? So this disorder area, it will move from one place to another. Okay, and the moment it will move, also this all the lattice structure also it will move. Okay, again it is moving from here to here, then again it is moving totally. So that means this is already the plastic deformation is happened there. Okay, so I mentioned there, and whatever the changes here, for example, this area or this length, for example, these are known as the Berger vector. Okay, if you remember that one. And the Berger vector also, I put one definition maybe for you, maybe if you do not remember that one. It represents the magnitude and direction of the lattice distortion. Okay, whatever the lattice distortion happened from here to here, because this length from here to here, resulting from a dislocation in a crystal lattice. But this is a quantitative or the magnitude it has. So you can tell that, for example, B, normally the Berger vector we are representing as B. So B, so then it will be a quantitative data or it has some magnitude, right? Is it clear? Yeah.
Yes. So
Yes, sir.
So now I put one more slide here for the direction of the dislocation motion. For example, if you know the edge dislocation and the screw dislocation, with the help of both edge and the screw, also you can move from one place to another. For example, if you will see the schematic diagram here on the top. So I mentioned also, you know, what is the basic meaning or the basic definition of edge dislocation and the screw dislocation. You can just have a cross check this one because whatever you have studied in the past. So you see here two things only you have to remember. The edge dislocation line moves parallel to the applied stress. Okay, so that means if you have the edge dislocation here, this line is parallel to the applied stress. The applied stress you are giving here. So this should be parallel, this line and this line. So in this way also your material or your like you know the place also you can move from here to here. Okay, and this area and this length is known as the Berger vector, right? And similarly, whatever the screw dislocation line moves perpendicular to the applied stress. Okay, so you can see here, this is screw dislocation. The screw dislocation is a topological defect of a crystal lattice. If one moves around the dislocation, the lattice plane shift by one layer. Okay, so that means if it is shifting from here to here, so that means one lattice plane is again it is moving. One lattice plane is moving, and whatever the direction of motion here, and this direction of motion is perpendicular to the applied stress here. Okay, this is not in parallel to the line. Okay, if it is parallel, then it is known as the edge dislocation. If this is perpendicular, this is known as the screw dislocation. Okay. Yeah, somebody is asking any question? No. Yeah. Okay. Yeah. Then next is we should know about the sleep system. Okay, so what because we know about how the sleep actually happen, but we have to understand what is the basic meaning of sleep system. And if you want to consider the sleep system, then in between the sleep system we have the sleep plane and we have the sleep direction. Then if we combine both sleep plane and sleep direction, this is known as the sleep system. Okay, so whenever we are doing any kind of sleep, like you know, from one place to another, so we have to consider the sleep plane. Maybe based on this also we will make maybe one or two numerical. So one is sleep plane and second one is sleep direction. The total we have to consider a sleep system, and the sleep system depends upon the crystal structure of the metal. You cannot tell that all the like you know that's why I'm telling if you have different kind of material, for example, the what I told about the crystalline and the amorphous material, this depends upon the crystal structure of that material. And the sleep plane is the plane that has the most dense atomic factor, that is the greatest planar density. If it will, the sleep plane, when we are talking about, it has the atomic packing factor, whatever, I do not know whether you remember that one or not, it will be a dense one. And the sleep direction is most closely packed with atoms, highest linear density. Okay, so these are the some of the factors, but at least you have to know that the sleep system means it consists of the sleep plane and the sleep direction. So now one more good thing is here, if the stress to cause the sleep is very high. So that means whenever you have the sleep you are happening or you are making, so what is the basic aim, why it is happening? If you have the internal stress there or if you have the stress there, that is the critical resolved shear stress is very high. Okay, we will talk about the critical resolved shear stress, what is that CRSS. Okay, so why this sleep is happening? So if you have the internal stress is inside or the shear stress is inside, then only you will find the sleep. Otherwise, you cannot find because this is like you know a fixed one. Your crystal structure is fixed one. It will not move. So if you have inside something, then only you will find the sleep, right? And also I mentioned at a higher temperature, most sleep systems may become active, and hence polycrystalline materials which are brittle at low temperature may become ductile at high temperature. Okay, and sometimes also happen why we told that how to remove that internal stress. You have to go for heat treatment. That means you have to increase the temperature. So that's why I mentioned that at a high temperature, more sleep system become at active, because sometimes if you are making some chemical reaction, let's say you are doing at room temperature, but the moment you are increasing temperature, your reaction rate will be faster. Okay, so similarly here also, when you have at a high temperature, also it will be your all the sleep system, it will be much more active there. So we have to consider the single crystal, we have to consider the polycrystal also, right? Fine.
Yes, sir.
Okay. So then some of the sleep system I just mentioned, you have to, for example, if you have, that's why I told, if a different crystal structure you have, so your sleep system is also different. Okay, so we are not going detail about, but how it looks like and how you are writing the sleep plane. Okay, so in this bracket you have to write the sleep plane, or maybe the square bracket also you can put, and the sleep direction you have to write like this. Okay, and the number of sleep system you have to calculate how many. For example, in FCC crystal, this is 12 sleep system, and HCB this is 3. So you have to calculate. So we are not doing how many sleep system are here. Normally, if you want to study maybe in material science, I think the beginning of the your BTech, I think you have studied that one. Just only I want to show these are the examples of the sleep system. Okay. Yeah. So now this is important that we some of the photos or schematic diagram I have shown you how the sleep actually you are creating with the help of that from one place or the one region to another region with the help of the Berger vector. But now also little detail, if we want to study how we will make it, how does the motion of dislocation lead to a macroscopic shape change? Okay, so that means from one shape to another shape, how actually it is changing. Okay, so just I put one example. When one bend of rod of aluminum to a new shape. Okay, so if you have a aluminum sheet, let's say a square shape, but you want to make it a rhombus-like structure, how it will make? So your net shape change will be from this square to a rhombus kind structure. Okay, so if you will see the next schematic diagram here, so you can see here. So I mentioned here this is the crystal structure here, and this is moving from this side to this side. Okay, so this is dislocation formed by pushing a plane. So that means you are giving a force there, or you are pushing there, and this will change from one plane to another, or it is moving, right? And the moment it is moving, so you will find this kind of structure here, because initially it was like this, and the moment it is moving, so you will find this space is empty here, and you are finding this space, and this length is known as the Berger vector. So I mentioned here the step formed when dislocation leaves the crystal. Okay, so this area now it is moving to here. And if you have the one plane, actually it is moving. So similarly, also you have to think about, because your total shape, net shape, it will change from the rectangle to a rhombus, right? So then if you want to change this one, then also similarly, you have to change this one, this one, this one, everything. The moment it will change everything, then you will find this kind of rhombus structure. Okay, so this is the second plane. The second plane, when changing, you are finding this kind of structure, right? And the moment you have three plane and fourth plane, then accordingly you have to go in this way. Okay, so that means you can imagine, because you have to imagine how it will change from a rectangle or from a square shape. You have to make it a rhombus, and the moment it is changing like this accordingly, then you have to the final shape. You have to go like this. Okay, all the planes you have to move from one to one. So the sequence of events finally leads to deformed shape, which can be approximated to a rhombus now. You cannot tell very exactly, but we are giving just one case study or one example. So you have to do like this. Then only it will change from one place to another. Right? Is it clear now? So now the plastic deformation, everything is very clear. Okay. Yeah. I'm all fine.
Yes, sir. It's fine.
Yeah. So next one, when you have the dislocation or when you have the stress moving from one place to another, so now we have to understand what is the mechanism. Now just we understood that this it is happening like this, but what should be the calculation, or what are the basis you are working with? So you have seen that there is a critical stress required to move a dislocation. So that means if you have a dislocation there, something is there so that it can push. Okay, if there is nothing, then it will not move. So if you have a critical stress is required to move a dislocation. At the fundamental level, the motion of a dislocation involves the rearrangement of bonds. So that means initially, if you will see the the perpendicular lines, you have bonds are there. So whatever the bonds initially, then you have to rearrange of that bonds. Then only you have to find, or you have to move the dislocation, and it requires the application of shear stress on the slip plane. When sufficient stress is applied, the dislocation moves from one metastable energy minimum to the another. So that means when the stress, for example, if you are standing there, so I'm pushing, okay, and the moment this is not sufficient, then you cannot move. Or maybe sometimes the wind is coming, so the wind is if not enough, then it cannot move from your place to another place. And the moment this stress is sufficient or the force is sufficient, then only you can move from one place to another. And the original model is due to the Perels and Navarro formula, and the sufficient stress which needs to be applied is called the Perels-Navarro stress, PN stress, or simply we known as the Perels stress. Okay, and this is the equation. You have the tau Pn equal to G e to the power minus 2 pi W by B. Okay, where is this G equal to the shear modulus, W equal to width of the dislocation, and B is the Berger vector. Okay, so these are the basic equation of the Perels-Navarro stress. To have, if you want to go for the sleep in the single crystal, normally if you have a crystal, for example, I have given one the schematic diagram. This is schematic diagram, and this is actually the zinc single crystal. If you want to give tension in both the side, so actually you will find this kind of structure. Okay, but if you put in schematic way in the macroscopic sleep in single crystal, so and this is the sleep plane actually, this the pink color, this is the sleep plane, and you are giving the force from upper side and the bottom side. So the moment you will see in the actually or typical in a zinc single crystal, you will find this kind of structure. Okay, so these are normally, because when we are stretching anything, we are just observing this is plastic deformation happen. But actually, when you are going toward any microscopic test or maybe any kind of high resolution microscope, then only we'll understand how actually it looks like. Schematic diagram is very easy. You can just predict and you can just tell. But how it originally looks like in the single crystal, you have to find like this. Okay. Okay. So this one is important. We have to think about what is the basic meaning of the critical resolved shear stress, and also we have to understand what is resolved shear stress. Okay, so both are almost same. So I mentioned here the resolved shear stress is component of the applied stress that causes a shear on a given plane in a given direction. Okay, so that means you are giving that stress to make it from one plane in a given direction. Okay, whatever we have discussed in the past. And what is the CRSS? The critical resolved shear stress is the minimum shear needed. Okay, if you are giving the minimum shear, so what I told just now, if you are giving the minimum and it can move or it can create a dislocation there, so this is known as the critical resolved shear stress. So if you will see the schematic diagram here, okay, so you have the stress you are giving here on the top. Okay, and this is the slip plane. So normally we are thinking about this one is A dash is the slip plane, and stress force by area, and this is the slip direction. Okay, and this tau, and this one is making an angle of the stress is known as the phi, and the slip plane. Okay, and this is making an angle of the stress is known as the theta. So I mentioned here the shear stress. Okay, whatever the shear stress we have the inside or is required, this is known as the tau. And then the slip plane whose normal makes an angle of the theta with the stress axis, and along a slip direction, you have the angle of phi to the stress axis. Okay, the three things we are getting. And the area is known as the A by cos theta. Whatever the change in area, whatever we have, is normal area divided by the cos theta. Okay, and if you want to calculate the CRSS, the stress force by area, this one tau equal to, you have to remember this one, F cos phi divided by A by cos theta. And the critical resolved shear stress or the resolved shear stress here, sigma cos theta and cos phi, this is also known as the scheme factor. And you have the yield strength. If you want to calculate the how much of yield strength, sigma y equal to tau CRSS. Okay, so sometimes also you do not much more think about the tau RSS, what is tau RSS and what is tau CRSS. Okay, so this is the minimum stress you are requiring. Okay, so all the equations are almost same. And the yield strength sigma y equal to tau CRSS by cos theta and cos phi. Okay, is it clear? You can write it the equations. Maybe based on this, we will make one or two numerical. Just you can write the stress, force by area, and tau you have to write out F cos phi divided by A by cos theta, and tau RSS, okay, equal to sigma cos theta and cos phi, okay, and yield strength equal to sigma y equal to tau CRSS by cos theta cos phi. Okay, so if you want to write what is theta and phi, so you can write here the theta, the tau equal to the shear stress. Again, I'm writing, telling the tau equal to the shear stress. Okay, and theta is the shear stress on a slip plane. Okay, theta is shear stress on a slip plane and making an angle of theta, and the shear stress is making an angle of the slip direction is known as the phi. Okay, so phi is making an angle of slip direction. In somewhere it is mentioned gamma. Okay, is it fine?
Yes, sir.
Yes, sir.
Yeah. So now the question is, just you can write. Yeah. Consider a single crystal of BCC iron oriented such that a tensile stress is applied along a 0, 1, 0 direction. Okay. First question, compute the resolved shear stress. Compute the resolved shear stress along a 110 plane and in a 1 bar 1, 1 direction when a tensile stress of 52 megapascal is applied. You can make the first question. Then if the second question, if slip occurs on a 110 plane and in a direction of 1 bar 1, 1 and the critical resolved shear stress is 30 megapascal, calculate the magnitude of the applied tensile stress necessary to initiate yielding. You can write what are the like now what you can find out in which way, what should be the equation is required also. If you can do it, you can do. Otherwise, if you do not, just you can think, then you can tell me. So you have to find out the angle first, theta and phi. So can you find out theta and phi if you have the slip plane and the slip plane and the direction?
Yes, sir.
No or yes? How you are doing the theta or the phi? Any equation? Do you know? If you have the direction and the plane? No? You remember your material science? No one? Amal?
No, sir, I don't remember.
No? Okay, okay. So I will just show you one, then you can do. Okay. So if you have, for example, if you will see here, consider a single crystal of BCC iron oriented so that a tensile stress is applied along a 0, 1, 0 direction. Okay. So if you remember U1, V1, W1, normally you want to, based on this, you want to calculate. Okay. So if you have the U1, V1, W1 equal to 1, 1, 0 plane, because you have a plane. Okay. Then second, you have a direction 0, 1, 0. Okay, so if you want to calculate cos theta normally, cos theta equal to cos theta, because I mentioned it theta here. So cos theta equal to E1 U2, you know, this E1 and into U2 plus V1 into V2 plus W1 into W2 divided by root over E1 square plus V1 square plus W1 square into U2 square plus V2 square plus W2 square. this equation is already derived in your material science. Okay, so we are not going detail the derivation because it will take time. So only just you can calculate like this. So the moment you will calculate everything you have, E1 you have, V1 you have, W1 you have, then similarly U2, V2 and W2 you have. So you can calculate theta. Can you calculate theta?
Yes, sir.
Yeah, if you can calculate theta, then you can go for phi. In the similar formula you have to do, but you have to take the plane and direction, it will be different. How much theta is coming? 45?
Yes, sir. Calculating, sir.
Yeah, yeah. Okay. Other students, are you getting? Vishnu? Pranav? Mithran? Only Amal is responding. No other student. Anirudh?
Yes, sir.
Yes, sir, we're getting the value of theta.
How much?
So theta is 46, sir.
45? Yeah, 46.
45, sir.
Yeah, okay. Then calculate the phi. But only you have to think now what should be the the plane and the direction. So in your schematic diagram, it is already given there.
Sir, is 5 some 35.3 degrees?
35. What is the slip plane and slip direction you have taken?
So theta I got as 45.
No, that is okay. But you have taken in case of theta, E1 V1 W1 equal to 110 and U2 V2 W2 010, right?
Yes, sir. Yes, sir.
So what about in phi?
Okay, sir. I think I made a mistake, sir.
Yeah, so you have to change, and one should be same, other should be changed.
Okay, sir.
Okay.
Should it be -111, sir?
Yeah, -1, 1 second. -1 1 1.
Okay. And the other will be 010, sir.
010, yeah, yeah. So you have to remember that one, which one I told in the beginning. 1 second. This thing. Okay, so you have to understand the angle between the stress and the slip plane, and second one is angle between the slip direction and the stress. Okay, otherwise if you will confuse them whether you are taking theta or gamma or phi or gamma, that is different thing. Okay, but you have to write very clearly that it will be between the slip plane and the stress, and it will be between the slip direction with the stress. Okay, if you are clear there, then you can put your theta and phi. Answer will be same, of course. Okay.
Okay.
So that's why better to do when you are doing any kind of numerical based on this. So make a schematic diagram immediately so that you will write very clearly. For example, here it is mentioned, you can see here the phi, actually the slip direction here 1 bar 1 1, and you have the applied stress direction 0 1 0. Okay, so similarly here also slip plane is theta 110 and the 010. Yeah, Johan. Bernard. Few students joined now. How much is 5? Sai, are you doing?
Sir, doing, sir.
Yeah, yeah. Aditya.
There's next.
I is 54.7.
How much?
54.7.
Yeah, yeah, 54.7. Yeah, fine. The next, what you have to calculate? Compute the resolved shear stress. Okay, so in the first A point you can write, compute the this one, compute the resolved shear stress. Okay, so how much will be the resolved shear stress? What is the equation? Tau RSS equal to
Sigma cos theta cos phi.
yeah, sigma cos theta cos phi. Okay, so sigma is given. Tensile stress is how much? 52 megapascal. Okay, so that means 52 is given. Then you have theta, you have phi. So cos theta, cos phi.
Sir, somewhere around 22 MPa, something like that it's coming.
22. Yeah, 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 yeah.
Is it correct, sir?
Yeah, yeah.
Okay.
Okay. So if tau RSS you have calculated, then second question, what is asking? Calculate the magnitude of the applied tensile stress necessary to initiate yielding. Applied tensile stress. So what will be the equation? Sigma y equal to this one, yield strength. Sigma y equal to tau CRSS divided by cos theta cos phi. Okay, so tau RSS you have already calculated. So now tau CRSS divided by cos theta cos phi. So tau CRSS is given, I think. Okay, so how much it will be? Tau CRSS is given. Yeah, this is 30 megapascal. Okay, so 30 megapascal divided by cos theta cos phi.
So 73 some
Yeah,
point.
73.4 megapascal.
Okay.
Yeah, just you can cross check. Okay,
Yes.
so in the first slide I have mentioned theta equal to 45 degree. Then phi equal to for 54.7. Maybe I do not know whether you have 54 or maybe you told something. Okay, Then you have the tau RSS equal to 21.3 megapascal. Okay. And then you have the sigma y equal to 73.4 megapascal. Right? Everybody is getting the same answer.
Yes, sir.
Yeah.
Not exactly that
Yeah,
number.
it's okay. It's okay. 0.1, 0.2, or maybe 0.5 is also no. The steps should be like same. Okay, maybe for example, we are calculating theta and phi. If they are not asking the angle, if you will prepare the angle, this is good. But some people they can do like cos theta equal to this much, sin theta equal to this much. Okay, but not this is not the right way, because you have to find the angle first. Angle is important there. Okay. Otherwise, some people they can write cos theta equal to this much and cos phi equal to this much. But find the angle, then put the cos theta. Okay. Otherwise, somebody will tell what is cos theta, right? Okay. So next, one more question, small one. Determine the tensile stress that is applied along the 1 bar 0 axis of a silver crystal to cause slip on the 1 bar 0 1 bar 1 bar system. The critical resolved shear stress is 6 megapascal. Okay, so that means you have to find out the tensile stress in the bottom. Okay, so just only 2 lines I have shown. You can just do, then I will show the answer. So again, you have to go for, the theta and phi. Similar way, but only you have to find out which one is slip direction, which one is slip plane, then it will be easy.
Sir.
Yeah.
Sir, till finding cos theta, cos phi, okay, sir. But after that, what we should do, sir?
Then you have to find out what is it is asking. The critical resolved shear stress is given 6 megapascal. So what is theta?
Oh, okay.
You have to calculate, na? You have to calculate, because if you have the theta, then you have to phi. Then critical resolved stress is given 6 megapascal. You have to find out the tensile stress. Okay.
Yes, sir.
So just you can calculate how much is theta, or maybe cos theta. Anything is okay. Cos theta you can find, then cos phi you can find, and then you have to find out the tensile stress sigma. Okay. Amal, it's okay.
Yes, sir. Yes, sir.
Okay. Vishnu, are you doing? You are silent this time. Dia, Ayush. All the students are getting senior nowadays, right? Harish.
Sir, cos theta is somewhere around 0.47, sir.
0.47.
Yes, sir.
1 second, because I have not calculated actually. Okay, you can go for 5. Just I will tell. Maybe I will just calculate. Yeah, 0.82, right?
Sir, I got 0.47, sir. I'll check once again, sir.
What
Sir,
is the you have given the axis?
Sir, 0.81 only, correct one, sir. I made a mistake.
0.82, na? Yeah.
Yes, I made a mistake.
Yeah. Then you can go for the 5. Any other is getting the same answer what Sai got?
Sir, what's the theta angle, sir?
Theta value is 0.82.
Okay, sir.
Yeah, then you can go for the 5.
Yes, sir.
Is it hard, the numericals? Nihar? Vishal?
No, sir, they are not hard.
Okay.
Sir, cos phi is half, sir.
Half, yeah, 0.5, yeah. Then the next point is if you have the critical resolve stress is given 6 megapascal, then you have to calculate the tensile stress. Yeah, phi everybody is getting 1/2 or 0.5.
Yes, sir.
Okay, okay, fine. Then you can find out the tensile stress if this CRSS is given 6 megapascal.
Sir, 14.69.
Yeah, fine. But unit you have to write. Do not miss the unit.
Okay, sir. Okay, sir.
Okay, so steps. Again, I'm repeating whenever you are doing any numerical, you have to write the given first. Okay, what are the values given with unit? Then you have to what to find out. Okay, so one step again you have to write. Let's say find out angle. Let's say theta or maybe angle phi. This angle, but you have to do not write only theta equal to this or phi equal to this. You have to write what is theta in text. Then comma theta equal to this much. Then the text. Then phi equal to this much. So everything will be clear. Because if you are writing theta, then I will not, of course I know, but what I will, how I will know that you are writing theta is this one. Okay, you have to write very clearly. So, the teacher will check everything in the systematical way. But if answer is something plus minus wrong, you do not need to worry. But it should not be so, big deviation. Okay. Yeah. Okay, you can see. So I calculated cos theta. Okay, so cos theta, if you calculate, this is the equation, and you have to find out this is around 2 by root over 6, so equal to 0.82. Okay, you can write. Maybe I forgot to write. And then second, if you want to calculate the phi equal to 1/2 equal to 0.5. So you have to calculate the tensile stress sigma equal to tau RSS by cos theta cos phi 6 by and the 2 by root 6 into 1/2. You will get 14.7 megapascal. Okay. Yeah.
Yes, sir.
Yeah. Any question up to now?